Hello and welcome back to my channel. Today we're going to be talking about increasing or decreasing intervals. So when we're talking about increasing or decreasing, what we're really looking at is the slope of a function. So consider the function f of x above. On what intervals is f of x increasing? On what intervals is f of x decreasing? So when we're looking at functions like this, we are really wanting to look at the slope of our function. So increasing means that our slope is positive. So we're looking at this portion of our graph here between 2 and 5, and the portion of our graph from 7 on. One of the things that we can talk about with increasing or decreasing is some people include the endpoints, some people don't include the endpoints. Either one's kind of okay. When we include endpoints, we're not necessarily saying it's increasing at 2 or it's increasing at 5. We're just saying between 2 and 5, it's increasing. I personally like to write it where it's not including, so that way I don't confuse myself later on. So between 2 and 5, we are increasing, and 7 on. The reason why people include it a lot of the times is because we define increasing as the y value that comes next is bigger than the y value that came right before it. So in all cases, the y value at 2, which is -1, is going to be smaller than the y value at 2.1. So we could put the equal to and it would still be accurate. When we are decreasing, we're looking at the same thing except for we are looking at where the slope is negative. These are our other pieces on our graph. So between -3 and 2, and between 5 and 7. When we are looking at increasing or decreasing, one of the things that we really want to remind ourselves is that we're looking at how things are changing. We're looking at that rate of change. So the thing that is going to help us the most is the rate of change, which in our case is the derivative. Okay, so we need to talk about critical points or critical values. So if f of x is defined at x equals c, then f of x has a critical point at x equals c if f prime of c equals 0 or f prime of c is undefined. So we're looking for when things are 0 or when things are undefined. So let h of x equal x over x plus 2. Find any values of x where h has a critical point. So we're going to take the derivative of h of x. The derivative of x is 1 times x plus 2 minus the derivative of x plus 2 times x, all divided by x plus 2 squared. This gives us x plus 2 minus x over x plus 2 squared, which gives us the fact that h prime of x is equal to 2 divided by x plus 2 squared. Okay, we want to know when this is going to equal 0. Whenever we have a fraction like this, in order for our fraction to become 0, the numerator has to be equal to 0. There's no way that 2 can equal 0, so h prime of x never equals 0. But we still need to think about undefined. So if we think about what happens to our function h of x, or h prime of x, sorry, at our function, the denominator can't be 0. So if for some reason we get x of -2, h prime of x is undefined, at x equals -2. The other thing that we need to kind of keep in mind is that what happens when we put in -2 to that x value for h of x. So when we plug in -2 for h of x, we are going to get an undefined function. So because h of -2 is not defined, we can say that there are no critical points for h of x. Okay, let f prime of x equal x minus 1 cubed times e to the 2x. Find any values of x where f of x has a critical point. So critical points happen when we have our function equal to 0 or undefined. We don't have any division here, so there's not really any places where our function is going to be undefined. And we don't have a square root in here, so when we plug in negatives, it's still going to be fine. So we are going to set this equal to 0. So 0 is equal to x minus 1 cubed times e to the 2x. That means one of our two pieces here needs to be equal to 0. One of the things that I can say off the bat is that this is never going to happen. E to the 2x is never going to equal 0. So we can kind of ignore that piece. The thing that's going to make x minus 1 equal to 0 is 1. So if I take the cubed root, I get 0 is equal to x minus 1, and 1 is equal to x. So 1 is a critical point for f of x. It's a critical point at x equals 1. Consider the continuous function f of x. If f prime of x is greater than or equal to 0, then we can say the function is increasing. If f prime of x is less than or equal to 0, then we can say the function is decreasing on that interval. That equal to 0 is that part where we can kind of include the equal to in our interval, but sometimes people are a little bit weird about it. It just kind of depends. So to find where f of x is increasing or decreasing, we do the following. Find f prime of x, set it equal to 0, find those critical values, or when it's undefined, and then we're going to make a sign chart to kind of test out some stuff. So here's the thing. If we are given a graph, then we don't need to do a sign chart because the graph is our sign chart. So we have this function g of x, x squared minus 3x minus 21, and we are going to decide when it's increasing or decreasing. So the first thing we're going to do, find the derivative. So g prime of x, we have 2x minus 3. We need to find critical points. So we're going to set this equal to 0. There's no division, and it's a linear equation, so we're not going to have anything that causes the derivative to be undefined. So we get 3/2 for our x value. This is when we kind of go back to, just like with straight line motion, I do my table a little bit differently. So I have g of x, g prime of x, and x. You can make your table whatever you would like. So the one piece that we know for sure is that when x is 3/2, our function g prime is equal to 0. So this is that piece that we really need. So now we need to look at both sides of 3/2 to find out information. So when I am looking at my function, I can pick 0 as one of my things. 3/2 is a little bit bigger than 1.5, but less than 2, so I can pick 2 for my other one. We are going to plug in our value. We don't really necessarily care about the actual number we get, we really care about the sign. So if I plug in 0 for 2x minus 3, I get 2 times 0 minus 3, so negative 3. I only care about the negative. And then on the other side, if I plug in 2, 2 times 2 is 4, 4 minus 3 is 1. So we get a positive number here. When I'm looking at this function, or this table, what this tells me is that everything up to our 0 for our derivative is going to follow the same place. If it didn't, we would find more critical points. We'd find more zeros. So we are going to be decreasing every value of x before we get to 3/2. On the other hand, after 3/2, we're now increasing. So everything after 3/2, we are going to be positive, increasing. So the only other thing I like to add to this is just that visual of decreasing versus increasing. But once again, this is just a personal preference. I like it a little bit better because it just really focuses in on things that I need to know or need to write down. So g of x is increasing. On the interval of x being greater than or equal to is acceptable of 3/2. G of x is decreasing on x being less than or equal to 3/2. I know some people have a hard time, and I am actually one of those people, saying that 3/2 it's less than or equal to, and that's because we know when it's equal to it's 0, but it's still mathematically accurate based on the definitions that we have. This last page here are just some more examples. So let h prime of x equal x minus 2 times the quantity x plus 1 squared. Find the intervals where h is increasing. So we need to set it equal to 0. When we have this, we're going to use that zero product property to set each piece equal to 0. And we get 2, and negative 1 is equal to x. So now I'm going to go ahead and make my table. I have two x values that we need to deal with here, negative 1 and 2. So I'm going to have negative 1 and 2. I know my derivatives are 0 when we get to that, so I need to pick a number before. So I'm going to pick negative 2, a number after. I'm going to make it easy, 0, and then a number after 2. So now we're going to plug this into our function. We're really just going to be thinking about signs. So if I plug in negative 2 into my function, well, here, negative 2 minus 2 is going to be negative 4, so it's going to be a negative. Negative 2 plus 1 is going to be a negative, but it's going to be squared, so we have a negative times a positive. This tells me it is going to be negative. When we plug in 0, 0 minus 2 is negative, 0 plus 1 is positive, so we have a negative times a positive, which gives me a negative again. At 3, we have 3 minus 2, which gives us a positive, 3 plus 1, which is a positive, so we have a positive times a positive to give us a positive value. So I am decreasing, I flatten out for a second, I'm decreasing again, and then we change to increasing. So we are going to be decreasing when we are less than 2, and increasing when we are greater than 2. If we are answering a free response question, which all of these are technically, a lot of times we need to be a little bit more specific, and so we would say h of x is decreasing on x less than or equal to 2 because h prime of x is less than 0. So we just need to add that because that reasoning on why we did it. H of x is increasing. On x greater than or equal to 2 because h prime of x is greater than 0. Okay, let k of x equal to 2 times sine minus x. Find the intervals where x is, or where k is increasing and decreasing when we're between 0 and 2 pi. So just like before, we need to find k prime. The derivative of sine is cosine of x, and the derivative of minus x is a minus 1. So we're going to set this equal to 0 to cosine of x minus 1. So we have 1 is equal to 2 cosine of x, or 1/2 is equal to cosine of x. So we have these values of cosine of x when we equal 1/2. If we think about the unit circle, cosine is equal to 1/2 at pi over 3. And if I were to reflect it, which would be 5 pi over 3. So what I can decide is these x values of pi over 3 and 5 pi over 3. Cosine in itself is not undefined. It's a continuous function, so we don't have to worry about undefined. But we do need to look at these two places. So we have k of x, specifically k prime, and we have x. This is where we need to kind of think more about what's happening with our function than we do anything else. So cosine is a sinusoidal function. So when we think about what's happening with cosine at pi over 3 and at 5 pi over 3, we are at 0. When I am looking at things before pi over 3, cosine is positive, and it's bigger than 1/2 because we start at 1, so our values are going to be a little bit bigger than our function here. As we get to values after that, that's when cosine is between 1/2 and all the way back around our circle, all of those negative x values. So all of those are going to be less than 0, and once we come back around, we're going to have things bigger than 0. So we are going to be increasing when we are between 0, pi over 3, and 5 pi over 3 and 2 pi. K of x is decreasing when we are between pi over 3 and 5 pi over 3. This last problem here is going to be, consider the graph of f prime of x, where f prime is the derivative of f. Find the intervals where f is increasing or decreasing. So when we're looking at the graph of a derivative, we need to remind ourselves that our derivative tells us when we are increasing or decreasing based off of the sign. So we're looking at y values. If our y values are above the x-axis, then our function is increasing. If we are below the x-axis, then we are decreasing. So our function f of x is increasing between, or when it's less than -1, Our function is increasing, f of x is increasing when it is less than -1 and bigger than -1. And f of x is decreasing when we are between -1 and 1.